Good evening, everyone. My name is Wendy, and I'm the host of the seminar. Thank you all for joining us today. The following seminar is brought to you by nonprofit organization iExplore. iExplore is dedicated to providing an extensive online study and communication platform for students throughout the world. We have over 80 teachers and 500 students from multiple countries. Through free online individualized group courses and seminars like this one, iExplore helps students to interact, study, and grow together. I am honored to introduce our seminar presenter today, Devin Han. He's talented in computer science, coding, and tennis. He will be guiding us on a journey of binary numbers and its significance. Let's welcome Devin.
All right, thank you. So as she said, I will be leading you guys through binary today. Let's look at the agenda. So first, we're going to a dope question and solution related to binary. It's a very typical computer science problem and is usually taught in the introduction to binary. And then we're going to compare the number system, decimal versus binary, and the math behind them. And binary addition, which is how humans perform binary addition. And then we're going to logic gates, which is like how you make an electrical circuit perform some binary calculation. And we're going to look at how you combine logic gate to do some operations like addition, and then a little bit of JavaScript to test out our binary stuffs. All right, first, we're going to go into that dope question. So you're a king. You have 10,000 glasses of wine for feasting, but one of them is being poisoned. Now you have 10 mouses. They can drink as much wine as they want, and you can test the wines on them. So now take a moment to think about how would you use the 10 mouses to test which glasses of wine is being poisoned. You can only give wine to the mouse one time, but you can give as much wine as you want to one single mouse. All right, I will give you like a 30-second to think, and then I'll review the solution. Right, mice. I know it's not really humane to test them on the mice, but you're gonna have a feast a few hours later, so you don't want everybody to drink the poisoned wine. All right, another 20 seconds, just see if anybody could come up with a solution. All right, tip is using binary. The tip is to use binary, and each mouse could have as much wine as they want. All right, 10, 9, 8, 7. Well, you're giving them 100 wine each, but how would you know which wine is poison if you give them 100 wine each, right? You give them 100 wine, and what if one of them accidentally drinks the wine, and now you have 1 out of 100 possibility of which wine is being poisoned. Give one each. Well, all right, those are funny solutions, but yeah. How do I exit the full screen? All right, there you go. I'm gonna go back to my drawing pad. All right, so this is a situation we have now. We have 10,000 bottles of wine, and they're not drawn really greatly, and we have 10 mouse. Now, I drew these mouse really irregularly, so please don't criticize it. All right, we have 10,000 bottles of wine. So the most intuitive solution that we first came out with is like associating each wine with one single mouse, right? So this is very intuitive. So one mouse drink one wine, and if this mouse who drank this one died, then that means this wine is being poisoned, right? But the problem is we only have 10 mice, and if we have 10,000 mice, great, this solution works. But we only have 10 mice, and giving one single one to each mice only allow us to test 10 wines, right? 10 bottles of wines. So we have to think of a different solution. Now, we could give each, let me take a look at the chat. All right, won't they die if they drink so many wines? Well, you could just give them one sip and don't drink, they're bigger. Don't drink the one, the heck, rat are better than mice. I like cat, not mice. Well, so, okay. All right, yeah, yeah, that is true. All right, so we could give each wine a color to identify them. This is just how we identify the one. Now, we have an interesting idea here. If instead of giving each wine one single mouse to test it, we give each wine a pattern of mouse. Let's say for this yellow wine, now this is the important part you need to concentrate. For this yellow wine, we give it to these two mouse here. And for the blue wine, we give it to these three mouse here. Well, you might ask, well, Devin, now you're limiting your option even more. Now you can only test, you're giving you're giving one single wine to three mouse already. Isn't that limiting? Worse than associating each single wine with one single mouse? Well, actually, you could have multiple types of wine on the single mouse. So I let these three mouse drink blue wine, but I could also let these two mouse drink green wine. Notice how all these patterns are unique. The yellow wine is associated with the two first mice here, and green wine is associated with the second two mice here. Only two, and also blue wine also involves these two mice. It also has one single mice, another mice that distinguishes from the green pattern. So I hope you see that. In this way, you know what will happen? If the blue wine is being, let me just draw another red one. So maybe we could put the red one here. Now the red one is also a unique pattern. You see that it only has one, and this one is on the second wine. So this is also unique. All of these wine combinations on the mouse are unique. And since one is poisonous, that means if blue is a poison wine, then these three mouse will die. And since this combination is unique by itself, you know when these three mouse die, the blue is being poisoned, right? And if green is poisonous, I will go a little bit slower. Actually, I could just undo. If green is poisonous, that means these two mouse will die. All right, we're doing a count sign problem, not a historical question. Mix 500 bottles and have two mice drink each of the mix. What? Well, then you have 1 out of 500 possibility of what wine you have, which bottle is poisonous, right? You want an exact possibility. Take a two mixture of 500. Yeah, but you want the exact possibility. Now you're splitting it in half. Well, now you could only say this 500 wine, have wine that is poisonous. You don't know the exact stuff. All right, so I'll go back to my lecture, but that's a good solution on binary division. Like if you divide it up more, you could have more precise ideas. Yeah, so that is a good one. That's another solution, possible solution to this problem using divide and conquer, but we won't get into that because we're doing binary right now. And if who drew this? Thank you. And if the green wine is poisonous, which that will mean that these two mouse, this unique pattern of mouse, these two mouse, only these two, this green one was only applied to this two mouse here. And so that means these two mouse will die. Okay, all right, stop that. That means only these two mouse will die and no other mouse will die. And since this pattern is unique, when these two mouse died, we know that the green one is poisonous. Now notice how even though these two mouse also drink blue wine, we know that blue wine isn't poisonous because this mouse also drink blue wine, but he didn't die. So blue wine isn't poisonous. So if green wine is poisonous, and if these two die, then we know green wine is poisonous. And if red wine is poisonous, then only this will die. And notice how even though this mouse that died here, so if red was poisonous, this mouse will die. And even though this mouse had drank yellow wine isn't poisonous because this mouse will also drink yellow wine didn't die. All right, who's drawing? So hopefully you see that there's a pattern. You could just distribute the wines across different combination. Let's say if I have another wine of color purple, another one, then I could distribute it this combination. And if these two mouse died, since this combination is unique, I instantly know that the purple one is poisonous. And even though this mouse here drank three different cups of wine, I know that green and blue aren't poisonous since this different mouse here also drink green and blue and they didn't die. Only this each wine is being associated now to a pattern of mouse. And if that pattern of mouse had died, then that means that wine is poisonous. Any questions? Yeah, that's a good binary solution. That's a good divide and conquer solution, but we're doing like all right, no questions. All right, so cool, right? So now the problem is we want to know if there's enough unique combinations in this 10 mouse that allows us to test 10,000 100 wines, right? And how do we know there's enough combination? Well, for each mouse, I'm just going to clear out everything. For each mouse, we know that we could have either drink or no drink. So a drink or a no drink, right? So for one single mouse, we have two combination of wine. And that means having two combination allows us to test two wine. Now let me show you how this looks on paper. We could have 1. We could also have 0. In this case, 1 represents drinking the wine and 0 represents not drinking the wine. And you see we made two unique number here. We have this number and this number. And that means we can test two wines. You see how I could test these two wines here. So let me change the color with only one mouse. Let me just delete. Since each cup has the option of drink and no drink, I could test these two wines with only one mouse. Now the first option is of course no drink. So for the red wine, I'm just gonna do no drink. And for blue wine, I'm gonna do the drink option. And the way I test them is that if this mouse died, that means the blue wine, the green wine is poisonous, right? And the red wine is safe. And if this mouse didn't die, then I know the wine that he didn't drink, the red wine is poisonous and green wine is safe. So that's how you could test two different options, two different wines with one single mouse, since the mouse has the option of drink and no drink. So we have two here. And we have 10 mouse, so the second mouse is also a 2, right? A drink and no drink. And if you have studied algebra, you know that combining possibility is through doing multiplication, which makes sense, right? So you have this, you have the possibility of drinking this and combine it with not. So you have either this no drink and this no drink, or this drink and this no drink, or this drink and this drink, and this no drink and this drink. So this has two options and this has two options, and you multiply them and you get 4 options. Same for the another one, this one. this also has 2 options, and you multiply it by them. Now you have 8 options. And so what you would do is 2 multiply them all together, and which is 2 to the power of 10. Hopefully you have learned exponents before. If you're not, then it's fine. 2 to the power of 10 just means multiplying 2 by itself 10 times. And if we use calculator to calculate 2 to the power of 10, we get 10,024 different unique combinations. That means we could have 1024 different unique combinations. Like one combination could be this, where they drink this, and one combination could be these. So each wine, that means we have enough combination for each single wine to occupy a combination of mouse. So let's say we take the blue and we let them occupy this combination where these 3 mouse here drink the wine, and we take this black, we take this cup here and we give it purple, and we could let it occupy this combination where only this mouse drink wine. And since we have 1,024 different unique combinations, we can totally test 1,000 wines. And that's how you test 1,000 wines with only 10 mouse. Hopefully you get the part here. We just multiply all the possible combination together, and we get 1024. Yeah, of course. If you don't want, so Xiaomi found, if you don't want to listen, you are welcome to leave. Like this is I explained that this is a typical comp science problem, and the first second I literally just said this is a typical comp science problem that explains how you do binary. So like if you don't want to listen to this, you could go search up that on the website, and that will explain it for you. Yeah, of course. So this isn't my problem. This is a problem that is very typical in computer science. So like, all right, okay. I wasn't talking to anybody else. I was talking to Shouming Fang. All right, so let's go to the next place on our agenda, number system. So what is a number system? You can see I have a really lacking slides here. So I don't like using slides, so I will just use this again. We human count in decimal system where we multiply it by 10. So what we'll do is actually, now I'm drawing some gibberish looking stuff here, but you'll get it in a second. All right. So, oh, who drew this? By the way, I'm gonna re-enable the drawing. So like if you have any question, you're welcome to draw on the screen, because I saw people don't like disabling the drawing. So I'm going to enable the drawing and the annotation, so you can draw on the screen, but only do it if you have a question. All right? Deal? Okay. So because I saw people laughing, haha, you cannot draw. Well, now you can. All right, you can draw on the screen now, but only draw if you have a question. All right, this section is for you to draw, okay? Just don't draw outside of that section. Just draw whatever you want in this section. And if you have a question, just draw a big question mark here. All right, us human count in decimal system, which means that us human count in decimal systems, which means that, gosh, why? Wait, what? What do you mean? All right, whatever. Our human count in decimal system, which means that we're doing this, right? 321. And 321 basically means that we have 1 multiplied to the 10 to the power of 0. Now, if you if you're in algebra, you know that 10 to the power 0 basically equals to 1. So the first unit is just 1 multiplied by 1. And on the second digit, it's actually 2 multiplied by 10 to the power of 1. And 10 to the power 1 is just 10. So this actually means, this digit means 20, right? Right? I hope this is a fairly easy concept. Most of us learned this in elementary school. This 2 here actually means a 20. And this here is actually 3 multiplied to the 10 to the power of 3. James is requiring remote control of your screen. I'm sorry, I can't let you control my screen remotely. All right. This unit here is actually 10 multiplied 100, right? Fairly simple, right? They're just this digit multiplied to whatever 10 to whatever power. The unit digit 10 to the power of 0, this 10 to the power of 1, and this 10 to the power of 2, right? All right. So that's how decimal work. In binary, it's a completely different world. Now you might have asked, why would we use binary for computer? Why don't we just use decimal for computer calculations, right? Well, that is because it's really hard to manage all this current. I will show you in a second. In binary, for each unit, we only have 2 options, just like our mouse problem there. Remember the mouse? You could either drink or no drink. And by having multiple mouse, you allows for countless combination of numbers. When you have 10 mouse, you could actually count to 10,024. I mean 1,024. So for each binary digit, it's like the no drink and drink problem. You could have a 1, you could also have a 0. And this case, this 1 no longer means 1 to the, remember in decimal, this 1 here means 1 to the 10. 1 multiplied. I told you there's a circle and you're only allowed to draw in the circle. I will erase this. There's a box here and you're only allowed to draw in this box. All right. So in decimal, if we have a digit 1, like 1, right? You know it's 1, and if I have a 2, it's 2, right? So in decimal, we have actually 9 symbols. I mean 10 symbols, like 1, 0, 1, 2, 3, 4, 5. In binary, we only have 2 symbols, 1 and 0. It's just like the drink and no drink for the mouse. 1 and 0, drink and no drink. And here, if I have a 1, it doesn't, in binary system, it no longer means 1 multiplied by 10 to the power of 0. It means 1 multiplied by 2 to the power of 0, since we're in binary and there's only 2 options, drink or no drink. It's like that combination where we have each mouse has 2 possible combinations, and by combining all those mouse, we have different combinations. Hola. And 2 to the power of 0 is just 1. So if I have a binary where only have 1 digit, then it's only 1, right? And a binary of 0 means 0. Now, so far, it's similar to decimal, except we can't go higher than 1 in one single digit. And when we go to the second digit, stop requesting remote control. It's getting interesting. And this here means that now if we have 2 digits, remember that mouse? That mouse where we have 2 mouse and each can drink and no drink. So each mouse has 2 options, and therefore there's a total of 4 options for each mouse. Well, if we have 2 digits in our binary system, let me erase other stuffs. That means we could actually count 4 numbers: 0, 1, 2, and 3. If we have 2 digits in our binary system, let me show you how would I count it. So for the first digit, it is the number here multiplied by 2 to the power of 0. So we could either do 1 multiplied 2 to the power of 0 or 2 multiplied by 2 to the power of 0, right? I mean, sorry, 0 multiplied by power of 0, so 2 to the power of 0. So with one single digit, we could count 1 or 0. With only one digit. With two digit, we could do 1 multiplied by 2 to the power of 1 and 0 multiplied by 2 to the power of 1. And notice how we counted 1 multiplied by 2 to the power of 1 equals to 2. And this here is 0. And if we combine them, now the way you combine them is just to add them up like you did in decimal. Remember in decimal, you have tens digit and you just, the basic operation is just you take the unit digit and you take the tens digit and you multiply by tens digit by 10 to the power of 1, which is multiplied by 10. Like you have 21, then is 2 times 10 plus 1 times 1, right? Now in this case, it's fairly simple. We have, if I have 0, 1, it's actually 0 multiplied by 2 plus 1 multiplied by 1. And we can count, the way we count 1 in this case is just 0, 1, right? That's how we count 1. And we count, oh my God, who drew this? I told you there's a space for you to draw everything. So, and if we want to count it, the eraser is getting really small. I'm gonna zoom in. All right. And the way we count to 0, all right, I really need to disable annotation because, all right, for people who actually want to use annotation, I'm sorry about that. All right. The way we count to 0, why is this not drawing it? Who drew that big blank space? So that was actually pretty funny. The way we count to 0 is 0, 0, right? Since this is 0 multiplied by 2, and this is 0 multiplied by 1. We count to 2 by doing 1, 0, right? Since this digit here is actually whatever you have here multiplied by 2 to the power of 1. So we count to 0, we count to 2 by doing 1, 0. And if it's 1, 1, we could count to 3. This works by this unit digit here is 1 multiplied by 2 to the power of 0, which is 1. And this second digit here is 1 multiplied by 2 to the power of 1, which is 2. And we add them together just like we did in decimal, where we have 21, and it's basically 2 multiplied by 10 plus 1 multiplied by 1. We add them together and we get 3. That's how binary work. And it's like the mouse where no drink, and we have 4 combination. And if we have 3 digits, then it's 2 multiplied by 4, and we have 8 totally different combination. Yeah, what's the question? Yeah, what's the question? You can type it in chat. Did somebody raise their hand or? All right, I'll keep going then. And if I have third digit, this 3 digit yield me a total combination of 8. 4 digit you'd need a total combination of 16s, right? 2 multiplied by 8. So you can see that we can count all the way up to how much however we want by just adding a new digit. I won't do more counting with this binary now, so I'm going to go to the next section, which is how we add them together. Now we're gonna do some binary operation by hand. I'm gonna open a new instance of this. Let's do some binary operation by hand. Take this number, 1011, and can somebody guess what this number is? Like this. What do you mean disable certain people? I already disabled the annotation. All right, somebody guessed 11. Let's see it. All right, 1011. This means 1 multiplied by 1, which is 2 to the power of 0, right? This means 1 multiplied by 2, right, which is 2 to the power of 1. And this digit is supposed to be 2 to the power of 2. 2 to the power of 2 is 4. So this digit is 4. And 2 to the power of 3. What is 2 to the power of 3? That's 8. So this digit is 8. So we have an 8 here. 8 plus 0. Since this digit is 0, we don't count it. So it's 8 plus 0. And for this digit, I'm going to use a different color. For this digit, since this is a second digit, and it's 1, that means we have it. So it's plus 2. And for the first digit, since it has 1, that means we have it. And it's the first digit, it's just 1 plus 1. 8 plus 2 plus 1. Right, 11. Somebody said 11? Correct. Nice job, Tiffany. Nice job, Jason. Yeah, good job, guys. All right. Now we're going back to our binary calculation. It's really simple. I think most of you guys already know this, like instinctively, since this is similar to decimal calculation. So I have another binary, and this one is just this is 8, 1. This is 4, 5. This is 5. So the way we do calculation is that simple. Well, the way we do calculation with our hand is just add them up. And since 1 plus 1 equals 2, and we only have 1 and 0 in our binary symbol system, this became, we have a carry. And 1 plus this carry 1, still 0. And we have another carry. We have another carry, and this 1 carry plus this 1, 0, and carry. And this carry plus this 1, 0, and another carry, and 1. So I have 1, 0, 0, 0. This is not 10,000, okay? This is 0 to the 2 to the power of 0, 2 to the power of 1, you get it. 2 to the power of 3, 1 to the power 2 to the power of 4. So what is 2 to the power of 4? Well, 16. So now, where's my board? This calculation yields us a number of 16. And you can see that when we do decimal, we confirm that our calculation is correct. All right, really simple binary calculation. And binary calculation, really simple. Now we're going to get to some interesting part, because if you're a computer, you're certainly not going to do calculation like this, because you're not a human, right? If you're a computer. And where's my slide? Open another instance. We're going to cover logic gate. Logic gate is a type of special computing circuit that allows electrical flow to be altered when you enter some stuff. If we have an XOR logic gate, that means, let's say we have two numbers, 1, 0, 1, and 1, 0. If we have an OR logic gate and we perform OR on this two number, this will give us 1, 1. OR logic gate operated by you check for the you go by digit and you check for the first digit of the first number and you check. So if either of this digit is 1, you give a 1. And if one of this digit is 1, no, doesn't matter where, you get a 1. Even though this is 0, you get a 1. And this is same thing. If this is often written as addition, but it's not addition because the difference between OR and addition is that you have 1 and 1, and this will still give you a 1. It won't give you a carry. Right. So if both of them are 1, or if either of them are 1, we get 1. And in mathematics, we also call this operation union. It's like a union where if either of them are true, then you give a true. Right? It's like OR in programming, except this is bitwise OR. And all right, let's do it for AND. AND is like intersection in the mathematical term. So another 1, 0, 1, 0, 1. Guess what it will yield? It will yield 0 and 0 if you perform an AND on these two numbers. This is because AND is intersection, which means it will only result in a 1 if both of them are 1. So let's say you have a, so since this is 0, and even though this is 1, it will give you a 0. It will only give you a 1 if both of them are 1. So I have a 1, 1 here, and then this will give me a 1. So that's how AND work. Now those aren't addition, aren't subtraction, but they're simple enough to be built into a single computational circuit. Let me show you how would they be built into a circuit. So let me draw a circuit. Now I'm not a master at circuitry, so I'm just draw really short, and I won't show you battery and any other stuff. But let's say we have a bulb here. All right, not a really good drawing. And this bulb represents our output, right? If this bulb is lighted, it means 1. If this bulb is not lighted, it means 0. And we have a switch box here. Now, if this is an OR, our switch will look something like this. Let me get an eraser. This is how electrical circuit show. This is our switch number 1, and this is our switch number 2. You can take this switch like our input. So these two switches are basically our input. And if you know any circuitry, you will know that if any of this switch become turned on, then this light bulb will be turned on. So like it doesn't require both of the switch to be turned on to turn on the light bulb. That's how an OR work, where if only one single switch being turned on, then the light bulb will be turned on. Well, if none of them are being turned on, then of course the light bulb won't be turned on. The switch here is like our 1 and 0. In computer science, we represent 1 with a high current, usually by 5 volt. And we represent 0 by a low current, usually 0 volt. So that's how we represent 1 and 0 in computer science inside a computer. So in this case, we have an input of 0 and 0, and of course we result in an output of 0. And if we turn the switch on, so we connect the switch, and it's essentially we're giving an input of 1 here. The circuitry will flow. This is our battery. The circuit will flow, and our light will be turned on. So it will result, and when the light is turned on, it's essentially like resulting in a 1. Now, of course, this is not how exactly it might work, but this is how you could get an idea of how to build the circuitry. If we can communicate with computer with binary, well, you operate with your calculator with decimal, communicate with your computer with binary. Yeah, like machine code is written in binary, so you can write machine codes. All right, let me show you what an AND might look like. In an AND, you could have something like this. So this is AND now. A circuitry of AND might look something like this, where you have, this is your switch number 1 and switch number 2, your battery here, and your light bulb. So now you can see that only if both of the switches are connected, this circuit will be circuiting, right? And then the light bulb will be turned on. Boom, light bulb on. But if any of the switch, let's say this switch, is open, so it's essentially as having an input of, sorry, it's like having an input of 1, actually 0, and switch number 2 input of 1. Well, since this switch here is being turned on and this switch here is not being turned on, since this switch here is not turned on, we can't really have a flowing circuit, and that's why our light dies out. And in computer science, it is equivalent of resulting in 0. Only if you have both of them turned on, so I turn on both of them and the circuit flow, I get a 1. So that's how AND work. XOR is a bit more complicated. It is built with OR and AND. Let me show you how XOR work. In XOR, only if there's one of them that is 1, you will result in a 1. So you could only have one of them as 1. Let's say we have 0, 1 and 1, 0. In XOR, it will result you in a 1, 1. So input of 0, 1, 1, 0, it give you 1, 1. This isn't or AND per se, because in an OR situation, if you have, this is a OR situation, if you have an OR situation and you give a 1, 1, this will be true. This will be a correct calculation. But in XOR, if you give a 1, 1, both 1 here and 1 here, it will actually give you a 0. So it's a little bit more complicated. So the cases are 1 XOR 1 equals to 0. 0 XOR 1 equals to 1. 1 XOR 0 equals to 1. And 0 XOR 0 equals to 1. XOR is the instance where it's crucial to us for building a addition system in computer with circuitry. All right, let me show you how to build a circuitry computer that does the addition system that we just did. So let's build a computer. So we want to add these two numbers. How would we do that? Actually, make it more complex. We want to add these two numbers with circuitry, not by our brain, but with circuitry. This number here is 3. This number here is 1. So we want to add them together. The way we do that is, first, you see that we assume that this is input number A, and this is input number B. And this is our input number A unit place. We call this BI. And this we call it AI. So this is a unit place for our input. And in the resulting place, we could call this S and call this SI. And for carry, let's call it M. Let's call it C for carry. And notice how if we add 1 and 1 together, in our calculation, it's going to be 1, 0, right? Then this place will actually be 0. So this is a perfect XOR situation. Like say we want to add 1 and 1 together, this should be 0, and we carry 1 to there. And we add 1 and 0 together. Now this will be 1, and 0 and 1 this will be 1. But if we add 1 and 1, this will be an XOR situation where 1 and 1 doesn't result in 1, but instead result in 0. And we carry a value to the second place. So in this case, we can have an XOR circuitry here to calculate what will yield 1 and 1, and in this case 0. And to calculate the carry, we could just use an AND circuitry to calculate the carry, right? Since 1 and 1 equals to 1, and any other thing else like 1 and 0 equals to 0. So it will only result in carry if both of them are 1 and they exceed the symbol number that became 2. So then we will have a carry. And this carry is being calculated by AND, logic gate AND. So the way we add these two numbers is very simple. First, we do an XOR to 1 and 1. So 1 and 1 and XOR operation. And it's like we giving them to an XOR circuit. I forgot how to draw XOR on circuit, but and then since it's both 1 and 1, it results in 0. So this digit, we XOR them and give us 0. That's how we calculate it with computer. And we have another carry value, right? It says 1, 1. So to calculate what the carry value is, we input them into an AND machine. So 1 and 1, we calculate by AND, and result in a 1, right? And if we have a 1 and 0, then so assuming this is 0, then there won't be any carry, but this is 1, so we have a carry here. So our carry is 1. And then we'll just perform the calculation, the XOR to the carry and the 0 here. And so we XOR 1 with 1. And that will result in us in another 0, right? Since 1 XOR 1 equals to 0. And since we're doing 1 and 1, we use this carry to plus them together. And now we're gonna check if there's any carry between these two numbers with our computer. So we're gonna do an AND operation between this. So between this and this. So we're gonna do 1 and we now know that an AND operation will result in a 1 here. So we have another carry. And we don't have any digit here, so we're just gonna drop the carry. And this will become, this is second place, fourth place, and 1 0 0, which is 4. So I have 1 0 0 here. And this is how you use logic gate to calculate. So with that, you can actually build a computer in Minecraft or anything like that, or just use circuitry to build a simple calculator. My friend had done that before. So you just use redstone and place them together and make a lot of logic gate and then give input by giving redstone input. I'm not good at Minecraft circuitry, so I can't really give you advice on it, but this is the idea you use to build a Minecraft computer. And what's on the agenda? The next thing to do is JavaScript, but all right. All right. I'm just going to show you how to do binary operation in JavaScript. So this is, all right, it's an hour now? No, it's not an hour. We still have 15 minutes, 9 minutes left. I'm just going to quick do a show you how to do this in JavaScript. You can leave it out if you don't know JavaScript, because I'm not going to explain the syntax here. This is called a bitwise operator, just straight line here. And if we do a bitwise between 1 and 1, let's see the result. What happens here is underground it converted to binary, so we're essentially doing a or binary 1 or 1, and it looks the same, right? Because we're having 1 and 1 here. And we run this console.log. And this result us in 1, since 1 or 1 equals to 1, right? And if we do a 1 or 0, 1 or 0, 1 or 0 is also 1, right? Since remember the circuitry, this will also result in 1. And the AND is this symbol, logical AND. And what will happen now is that we're doing a 1 and 0. And if somebody remember what I just said, 1 and 0 equals to 0. So AND is an intersection and will only return true if both of them are true. So now you can see I did a 1 and 0, and this is 0. Let's have some more complex number like 2. So 2, actually 3. 3 written in binary is 1, 1, is 1, 1, right? And we want another number. So this is getting interesting. We want a 1. So essentially, we're doing a 1, 1 and 0, 1 operation. And let's see what will result. So 1 and 1, since both of them are 1, we give a 1. And since there's a 0 on the second digit, we will have a 0 on the second digit. So you can see it gives us the 1 for 3 and 1. So essentially, we're doing a binary bitwise, or and between these two numbers. These two numbers are being converted to binary underneath the hood. There's also an operator called bits shifting, which shift a number by some places. So let's say I have 11 here, actually 1, 1. Yeah, 1, 1, which represents 3, right? So essentially, we're having 0, 0, 1, 1, 1, since these are all not significant figures, and those doesn't represent anything. And we have 1, 1 here, which represents 3. And if we shift it by 1, that means we move the entire stuff to the right by 1 unit. We would have 1, 0, 0. Over on this unit, since we're shifting this entire stuff to the right. And now this is being moved here and it's being dropped. And so if we bit shift this 3 here, this 0, 0, 0, 0, 0, 0, 1, 1, will result in a 0, 0, 0, 0, 1. And the other one is being dropped. You can see it give us some 1. Now these are very useful operations to solve many compound problems. Like I can give you an example. In Unity, we have something called a layer mask, which is just a mask, and it is actually binary number. And the way you do it is the way you check to mask. Like, let's say, so if you want a layer of 0 to be turned on, you have a layer mask looking like this. And like if you want a layer of 3 to be turned on, you have a layer mask looking like this. So binary operations are very useful in many fields. And the way you check if this solution was 0, 0, 0, 0, 1, 0, 0. All right, that's it for this lecture. Thank you for coming.